In this lesson, we'll finish off learning target number 3. By the end of this lesson, you should be able to predict the products and write the balanced chemical equation, including states, for single displacement reactions using an activity series. Remember, single displacement reactions involve an element that's by itself, replacing another element in a compound. One analogy is a bodybuilder stealing a nerd's girlfriend. This is a good analogy because not all single displacement reactions work. The metal that's by itself has to be more reactive than the metal in the compound in order to steal its partner. This can be determined by looking at an activity series of metals. You have an activity series on the backside of the class periodic table. This activity series here is for metals. This box here is the activity series for halogens. It is not the continuation of this box because we ran out of room. We've listed the metals from the most reactive at the top to the least reactive at the bottom. In order for a single displacement reaction to happen, the metal that's by itself has to be higher in the list than the metal that's in the compound. If it's not, then no reaction takes place. Halogens can take part in single displacement reactions as well as metals. Here's an example where you have an ionic compound, sodium iodine, and chlorine gas, a halogen that's by itself. Using the activity series for halogens, chlorine is actually higher or more reactive than iodine. Therefore, it can steal its partner. The chlorine becomes sodium chloride and iodine gets kicked out on its own. Let's try some examples. We're given the following reactants. Let's determine if a single displacement reaction will happen, and if so, let's write the balanced chemical equation including states. Does a single displacement reaction happen between potassium and lead 2 nitrate? Let's look at an activity series. Because potassium is higher in the list than lead, it means that it's more reactive, and the potassium can steal lead's partner. Let's complete the balanced equation. The potassium will go with the nitrate. When I re-crisscross that formula, I get KNO3. Remember, just don't smush the elements together. It's not KNO3 bracket 2. Lead gets kicked out on its own. In order to balance the equation, I need to place a 2 here. And include the states. Because KNO3 is an ionic compound in a single displacement reaction and it's a product, I look up its state on the solubility table. Nitrate's not on the solubility table, so that means it's always soluble in aqueous state. I determine the state of the lead by looking at the color of its symbol. It's a solid. Pause the video and try out example 2, 3, and 4. Here are the answers for example 2, 3, and 4. Looking at an activity series, zinc, the element by itself, is higher than hydrogen, the metal in the compound. So a single displacement reaction will happen. The zinc will steal the carbonate, and I re-crisscross that to get ZnCO3, and the hydrogen gas gets kicked out by itself. My equation's already balanced, and I look up the states and include them to complete the question. Example 3. Magnesium is lower in the activity series than the sodium. That means that this reaction won't produce anything. If there's no reaction, you don't have to write a balanced chemical equation. Example 4. I check on the activity series for halogens. Here, I have a halogen that's by itself. And if you check the list, fluorine is higher than chlorine in terms of reactivity. So the fluorine can steal the sodium. In order to balance, I need to place 2's there and include states. Try out the practice questions listed in your textbook.